Welcome viewers to the third lecture for the online series of lectures for the course of linear algebra. In the previous lecture we discussed various results related to row reduced matrices. In today's lecture we are going to discuss row reduced echelon matrix. In some sense, it's a refined version of a row reduced matrix. Let me explain what I mean by a refined form. And m times n matrix R is called row reduced echelon matrix if first of all R is row reduced, so it has to be row reduced to be a row reduced echelon matrix first. Secondly, every row of R having all its entries zero occurs at the bottom of the matrix. I should say all row. It's better to say all rows, and this is occur, which means that all the zero rows of the matrix R should occur at the bottom of the matrix. We did not require this property for the matrix to be row reduced, recall. So if a row reduced matrix additionally satisfies some other properties, then we call that matrix row reduced echelon matrix. So this is one of those properties. Okay. Thirdly, if rows 1, all the way up to R are the non-zero rows of R, okay. Now we are focusing on the non-zero rows of R. All the zero rows of R are grouped together at the bottom of the matrix, okay. And for all the non-zero rows of R, so this third point applies to all the non-zero rows of R, okay. So if these R rows are non-zero rows of R, and if the leading one, the non-zero rows of R should start with a leading one, because it's a row reduced matrix, right? And so we are considering those leading ones, and if the leading one of row I occurs in column Ki, where I is from 1 to all the way up to R, then K1 is less than K2 is less than all the way up to KR, okay. So the leading one of the first row occurs at the K1 column, okay. Similarly, the leading one of the second row occurs at the K2 column, and similarly the the leading one of the rth row occurs at k sub r column. Okay, and if this is the case, then k1 has to be less than k2, and k2 has to be less than k3, and this way all the way up to kr. Okay, so this is the third requirement. So if a row reduced matrix satisfies these two additional properties, we call the row reduced matrix a row reduced echelon matrix. Okay, now we give you an example of a row reduced echelon matrix. This is our example 1. So two examples of row reduced echelon matrices are the n times n identity matrix So, for example, think about 3 times 3 identity matrix. Okay, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so it's a row reduced echelon matrix because it's a row reduced matrix because you see that all the non-zero rows of this matrix start with the leading one. Okay, and the columns that contain these leading ones have all other entries to be 0. Like this leading one of the first row is contained in the first column, and all other entries except for that leading one are zeros. Similarly, this one is contained in the second column, and all other entries except for that leading one are 0 as well. And for the third leading one occurring at the third column also has other entries to be zeros. Okay, this is 0, this is 0. So it is row reduced matrix. In addition to that, it doesn't have any 0 rows, so the second property does not apply in this case. And you see that the third property is also fulfilled for this 3 times 3 matrix, since k1 in this case is equal to 1, k2 in this case is equal to 2, and k3 in this case is equal to 3. And of course, k1 less than k2 less than k3 is fulfilled because 1 is less than 2 and 2 is less than 3. Okay, so it's a row reduced echelon matrix. Okay, so another example of a row reduced echelon matrix is the zero matrix, m times n zero matrix, denoted by a 0 superscript m comma n. Okay, so for example, we can take 2 times 3 0 matrix. Okay, like this. So it is represented by a matrix with 2 rows and 3 columns, all the entries of the matrix being 0. Okay, this is a 2 times 3 0 matrix, and you see that it's row reduced because it just contains 0 rows, so nothing specifically has to be satisfied for this matrix to be a row reduced matrix. And the other two properties, property B and property C, are trivially satisfied for this matrix. So this is a row reduced echelon matrix as well. All right, good. Now let me give you a non-trivial example of a row reduced echelon matrix. Okay, let me erase everything. A non-trivial example of a row reduced echelon matrix is given by the following 3 times 5 matrix consisting of 3 rows and 5 columns, 0, 1, -3, 0, 1 half, 0, 0, 0, 1, 2, 0, 0, 0, 0, 0. So first identify the 0 rows and non-zero rows of the matrix. So there is only one 0 row, and that is occurring at the bottom of the matrix. So we are good with property B. But before that, we have to check that it's a row reduced matrix, right? So identify the leading ones of the non-zero rows. So this is the leading one. This is the other leading one. Okay. There is no leading one in the third row, since the third row is just a 0 row. So the column containing these leading ones have all other entries to be 0, right? So this is a row reduced matrix. All right. Now let us check the other properties. So the second property is fulfilled because the 0 row is appearing at the bottom of the matrix, and for the third property, you see that K1 is equal to 2, meaning that it's occurring in the second column. So that the first leading one, the leading one corresponding to the first row, is appearing in the second column. Therefore, K1 is equal to 2, and the leading one corresponding to the second row, right, is appearing in the fourth column. So K2 is equal to 4. Since 2 is less than 4, we also have satisfied the third property of a row reduced echelon matrix. Therefore, this is a row reduced echelon matrix. Okay, good. So now we have our first theorem of this lecture. Theorem 1, which tells us that every m times n matrix A is row equivalent to a row reduced echelon matrix. Okay. So the variant of this theorem for row reduced matrix was proved in the previous lecture, which stated that every m times n matrix is row equivalent to a row reduced matrix, right? So now we have some additional properties of the row reduced matrix to satisfy, which make it row reduced echelon matrix. Okay, let us go over the proof. We know that, so this m times n matrix A, we know that A is row equivalent to a row reduced matrix by theorem 4 of lecture 2. Okay, like I said before. Now, by a finite number of type 3 elementary row operations, by what was the type 3 elementary row operations? Recall that it's just the exchange of any two rows of a matrix, right? By a finite number of type 3 AROs, which means interchanging rows of a row reduced matrix. So we consider that row reduced matrix which we obtain from this matrix A after a finite sequence of elementary row operations that we did in the proof of theorem 4 of lecture 2. Okay, we start from that matrix, and by a finite sequence of interchange of rows, okay, we can bring all the 0 rows to the bottom of the matrix. Okay, one can bring all the 0 rows, if any. If there is no 0 row, we are all good. We are all set, right? We don't care about these operations. But if there is any, we can bring them all to the bottom of the matrix by a finite sequence of type 3 elementary row operations at the bottom of the matrix. Bottom of the matrix. Okay. Okay. So that way, this matrix is going to satisfy the second property of a row reduced echelon matrix, property B. Okay. Now also, by applying finite number of interchange of rows on a row reduced matrix, okay, one can achieve the third property as well. Achieve the third property, property C, third property of a row reduced echelon matrix in a row reduced matrix. Okay. So we just have to apply the third elementary row operation finitely many times to make our row reduced matrix satisfy the third property of a row reduced echelon matrix, so that all the 3 properties of a row reduced echelon matrix are satisfied, and we have finally a row reduced echelon matrix obtained from the matrix A. Okay, good. QED, very simple. So all through the proof, we just applying one type of elementary row operations, the third type, just the interchange of rows. This type of elementary row operations is sufficient to convert the matrix into a row reduced echelon form. Okay, all right. So let me erase everything. So in lecture 2, we have seen importance of row reduced matrices in solving homogeneous system of linear equations, right? Because that was the desired form. We started with the matrix, an arbitrary matrix, and we put it in the row reduced form, and then we can compare the solutions of the underlying systems. Okay, and we saw that by means of theorems that the two systems have the same set of solutions, meaning that we after converting our original system to a desired form, we can conveniently solve the underlying system of linear equations. Okay, so it was important to convert a matrix into a row-reduced matrix that we have seen in previous lecture. Let us now focus on the system. So in this lecture we are focusing on the system Rx is equal to 0, where R is not just a row-reduced matrix, it's a row-reduced echelon matrix. It's a row-reduced echelon matrix. Okay. All right. Now let rows 1, 2, all the way up to R be the non-zero rows of R. Okay. It may not have all the rows to be non-zero, so we are assuming that 1, 2, all the way up to rth row are the only non-zero rows of R. Okay, and suppose that leading one in the ith row occurs at the kith column. Okay, where I is between 1 and R. Okay, good, and we can always do that since it's a row-reduced echelon matrix. The system Rx is equal to 0 then consists of R non-trivial equations. Okay, so all the 0 rows are trivial equations. 0 is equal to 0. Okay, so the only non-trivial equations are represented by the non-zero rows of the underlying system Rx equal to 0. Okay, note that the unknown x sub ki will appear only in the ith equation of the system. Okay, it's because x sub ki corresponds to the leading one in the kith column or in the ith row. So these variable or this unknown of this corresponding system corresponds to the ith row and the kith column, where the leading one is, where one of the leading ones is situated. Okay, and for that reason, since it corresponds to the leading one of the leading ones of the underlying row-reduced echelon matrix, it has to appear only in the ith equation of the system. Okay, that's the reason. We give it a we give it a name to distinguish these variables or these unknowns from the other unknowns of the system. We call x sub ki's the leading variables. The leading variables. Okay, to differentiate them from the other variables. So how many variables are how many leading variables are there in this system Rx is equal to 0? You can immediately see that there are only R leading variables or R leading unknowns in the system Rx is equal to 0. Okay, and they are all happening in these rows. Okay, so there were n unknowns altogether in the system, and the remaining n minus r unknowns, which are different from these leading variables x sub k1, x sub k2, all the way up to x sub kr are denoted by u1, u2, all the way up to u sub n minus r. Okay, it's immediate from this indexing that there are only n minus r of such variables. Okay, we call these variables, we call these unknowns or variables, unknowns, free variables. Okay. All right, so there are two types of variables of the underlying system. One type is called the leading variables, and the other type is called free variables. Okay, good. Now, using I can erase everything, I guess. Using the leading and free variables, one can write the R non-trivial equations. Okay, so we are concerned with the non-trivial equations of the system Rx equal to 0. The trivial equations are just 0 is equal to 0, right? Write the R non-trivial equations in Rx is equal to 0 in the following way. Okay, all right, so let's focus on the first row. Okay, so the leading one corresponds to the variable x sub k1. Okay, and you know that is expressed, this leading variable is expressed in terms of the remaining n minus r variables, and we attach these coefficients c1j's with the respective free variables uj's, where j vary from 1 to n minus r. Okay, so it's important to know that these c1j's have nothing to do, well, they have something to do with the original matrix R. You can read these c1j's from this matrix R, but you know it's better to think of these c1j's as separate coefficients attached to this unknowns, the the free variables of the system. Okay, so we are writing the xk1 appearing in the first row and the k1th column in terms of the remaining in terms of the free variables. Okay, is equal to 0. Okay, so this is how. So you take this matrix R, okay, and take its first row, and that will give you this equation. And in terms of one of the leading variable and the free variables. Okay, all right. So this is the first. This corresponds to the first row of R, and the second row of R will give you this equation. This linear equation: x sub k2 from j equal to 1 to n minus r. C2j, this 2 stands for the fact that we are considering the second row of R. C2j ej uj, okay, is equal to 0. Similarly, we go all the way down to x sub kr, and x sub kr plus sum over these numbers. C rj uj, j running from 1 to n minus r, and this is equal to 0. We set it to 0, and this is the system that reads off from this matrix R. Okay, the non-trivial equations corresponding to Rx is equal to 0. Okay, good. So this is what I have written down here. Here the Cij's. Here the Cij's are not to be confused. With the entries of R. But of course, Cij's for I equal to 1 to all the way up to R, and j is equal to 1 to all the way up to n minus r, can be read off from the matrix R, as we will see using examples. Okay. So the goal here was to write these R non-trivial equations resulting in from Rx is equal to 0. Okay. Okay, good. So we have this system of R linear equations corresponding to the homogeneous system Rx is equal to 0. All the solutions to the system Rx is equal to 0 are obtained by assigning arbitrary values to u1, u2 all the way up to u sub n minus r, and hence we call them the free variables, and hence they are called free variables. Okay. Okay, so let me write this system 1 again, which I erased a while ago. The first one being x sub k1 plus sum of all the terms containing c1j uj, where j runs from 1 to n minus r, and we set it to 0. The second one being x sub k2 plus sum over c2j times uj, where j runs from 1 to n minus r, and we set it to 0 again. All the way down to x sub kr plus sum over all the entries in crj. It is happening in the rth row, uj and j from 1 to all the way up to n minus r. Set it to 0. So this is the system of linear equations, reduced system of linear equations, right? And for each row, you see, for each equation of the system, you see that you are writing xki as a linear combination of the free variables uj's, right? J running from 1 to n minus r. You are taking all the linear. You're taking a linear combination of this n minus r free variables, right? The coefficient of the linear combinations are these Cij's, right? For this first row, they are just C1J's. Okay. And now, so you are free to choose the free variables, right? You can assign arbitrary value to the free variables and find the value of the leading variable in terms of those assigned for the assigned values of the free variables. Okay, that's what I'm saying. Okay, are obtained by assigning arbitrary values to these variables. That is why they are called free variables. Okay, now I give you an example. Let's consider the example of 1. Okay, so we are revisiting example 1, where we had this row reduced echelon matrix R to be equal to 0, 1, -3, 0, 1/2. Okay, that was the first row. The second row was 0, 0, 0, 1, and 2. And the third row was a 0 row. Okay. This is a row reduced echelon matrix. And what is the corresponding system? Rx is equal to 0. So so in order to form this, it's a 3 times 5 matrix. So you gotta have a 5 times 1 matrix, which is x1, x2, x3, x4, x5. Okay. So the number of columns of the first matrix has to be the same as the number of rows of the second matrix. So the second matrix has to consist. It should consist of 5 rows, right? And since we are just considering the matrix consisting of unknowns only, we have a column vector. Okay, and we set it to 0, and then we get the following system of linear equations. So by usual matrix multiplication that we learned in the very first lecture of this course, we see that we have x2 minus 3x3 plus 1/2 x5. I give a space here to know that to confirm that x4 is present here, but with the coefficient 0. Okay, that's why I leave this space blank. and that is equal to 0. The second equation is x4 plus 2x5 is equal to 0. Okay, and the last equation is just the trivial equation, 0 is equal to 0. So we don't write that. So this system takes this form for this particular example of R. Okay, and it can immediately be rewritten as x2. So this is a leading variable, and this is also a leading variable. So we are supposed to write the leading variables in terms of the free variables. So let us write x2 as a linear combination of these two free variables. Sorry, it was minus 3x3. Okay, so which gives 3x3 minus 1/2 x5, and the leading variable x4 is equal to negative 2x5. Okay, so this is the solution of the system, but now we can assign arbitrary values to this free variables. These are free variables. So identify your leading variables and the free variables. So the leading variables of the system of the system corresponding to this matrix are x2 and x4. So the remaining variables are the free variables. So let me write it here for you. Leading variables for this example are x2 and x4, and the free variables or free unknowns, if you want to call them, are x3, x4, sorry, x3, I forgot x1. X1 has to be, so everything else is going to be a free variable. So x1 is a free variable, the next one is x3, that is a free variable, and x5 also is a free variable. Okay, so let me erase this top bar. So now assign arbitrary values to the free variables. So we choose x1 to be equal to A, x3 to be equal to B, x5 is equal to C. Okay, we can assign any value to A, B, and C. We are free to choose these values, A, B, and C. And then x2 is equal to 3B minus 1/2 C, and x4 is equal to minus 2x5, which means minus 2c. Okay, so what is the solution set? You write the solution set as x1, x2, x3, x4, x5. This 5 tuple is your solution set, and the solution set for this system is given by A, and then this is x1, then you have to write x2, which is going to be 3b minus 1/2 c, and then you have to write x3, that's going to be b, and then x4, which is negative 2c, okay, and then x5, which is just c. So this is your solution set for the matrix R given by example 1. Okay, right, let me check if the solution set is correct. Right, it's correct. Good. Now I want to put a remark here following this example 1. So let me write it as a remark. which is an important remark. Let us at this moment, so we revisited the example 1. Let us focus back in the system. Rx is equal to 0. Okay. Right. So which we wrote as remember, which we wrote as, I'm writing it again, x sub k1 plus sum over c1j uj, j running from 1 to n minus r, and we set it to 0, x sub k2 plus c2j uj, j running from 1 to n minus r, we set it to 0, and all the way down to x sub kr plus j from 1 to n minus r, c rj uj, we set it to 0. Okay, this was the system. So if the number r of non-zero rows in R is less than 1, is less than n. Okay, n is the total number of unknowns of the system. Okay, which means that it is less than n means that there are free variables, right? If the number of non-zero rows is exactly equal to n, there is no free variable, right? So it is strictly less than n means that it certainly has got some free variables, right? Then the system Rx is equal to 0 has a non-trivial solution. Okay, what do we mean by non-trivial solution? Okay, so that's what I am explaining now. That is a solution. A solution is an n-tuple, right? In the previous example, the solution was a 5-tuple. So a solution in which not every xj is 0. Okay, that's what we mean by non-trivial solution. Okay, so a trivial solution means that all the entries in this n-tuple are 0. That's what we mean by a trivial solution. Okay, so what we are saying in this remark is that if the number of non-zero rows in the row reduced echelon matrix R is strictly less than n, then of course there is a non-trivial solution. Okay, let me explain why. This is because since R is strictly less than n, one can choose n minus r remaining variables u1, u2, all the way up to un minus r, these guys, arbitrarily to write xk1, x sub k2, x sub kr, okay, in terms of u1, u2, all the way up to u sub n minus r, right? According to this expression, we can do that. And when we are choosing arbitrary values of these n minus r free variables, we can choose anything for them, right? We can also choose non-zero values for them, so that this n tuple will not be identically a zero tuple, right? By which I mean that not all the entries in this n tuple will be zero. I can choose, of course, I can choose non-zero values here because they are free variables. I'm free to choose the values of those variables. Okay. So, in other words, there will be a non-trivial solution always. Okay. Okay. So whenever the number of non-zero rows of the row-reduced echelon matrix is strictly less than n, where n is the total number of variables, there will always exist a non-trivial solution of the system. Okay, so now we have the following theorem, which follows from this observation put in the remark. Theorem 2. If A is an n times n matrix and M is strictly less than n, meaning that the number of rows is strictly less than the number of columns of the underlying matrix A. Okay, then the homogeneous system corresponding to this matrix, the homogeneous system of linear equations Ax is equal to 0 has a non-trivial solution. Okay, all right, let's prove it. Let R be a row-reduced echelon matrix which is row equivalent to A, which we can always find, right, by means of theorem 1. A is any m times n matrix, and we can apply elementary row operations, a finite sequence of elementary row operations to convert it into a row-reduced echelon matrix. Okay, and theorem 1 guarantees that. Okay, so let R be that row-reduced echelon matrix obtained from A. Then the system the systems Ax is equal to 0 and Rx is equal to 0 have the same solutions. Okay, have the same solutions which follow from theorem 3 of lecture 2. So get back to theorem 3 of lecture 2. We'll see why these two systems of linear equations share the same solutions. Okay. In other words, they are equivalent systems, right? Equivalent systems of linear equations, so that they have the same solutions. So if R is the number of non-zero rows of R, because R is a row reduced echelon matrix, so you can immediately find the number of non-zero rows, right, in that row reduced echelon matrix. And if that number is so that we know that the matrix A that we started with had m rows, okay, and we applied the elementary row operations to convert it into a row reduced echelon matrix R. Okay, so if R is the number of non-zero rows of R, then of course R is less than or equal to m. Okay, which means that it can have at most m number of non-zero rows, right? It cannot exceed m, because that's what we started with. M is the number of rows of the original matrix. So the number of non-zero rows in the row reduced echelon matrix, which is equivalent to the original matrix that we had, should have number of non-zero rows to be strictly is less than or equal to m. Okay. Now, since m is less than n by hypothesis, we are given that m is less than n by hypothesis, r is less than or equal to m, and m is less than n. Therefore, we must have r is strictly less than n. Okay. All right. So the number of non-zero rows is strictly less than n, where n is the total number of unknowns. So now, from the remark that we had a while ago, it follows that it has a non-trivial solution, right? Then, by the remark mentioned a while ago, Rx is equal to 0 as a non-trivial solution. In other words, it has at least a non-trivial solution. A non-trivial solution. Okay. Therefore, and we already know that Rx is equal to 0 and the system Ax equal to 0 have the same set of solutions, right? So if Rx is equal to 0, this system has a non-trivial solution. So does the system Ax equal to 0, right? Therefore, Ax is equal to 0 has a non-trivial solution. Okay, good. That's what we wanted to prove. QED. Okay, so that's the proof of theorem 2. We take a break now. We'll be back with more results in the second segment. Thank you for attending the first segment of the third lecture.